because from the title, probably prolongation is not so, may not be very familiar to some of you. So let me start with the definition of this term, prolongation. So what we will consider a vector space. So V is a vector space of dimension n. Everything I already consider over complex numbers. Now consider a Lie algebra inside the Lie algebra of endomorphisms of V, the Lie subvarieties. Then for each non-negative integer k, I will define the prolongation in case prolongation of G. So that's the term to be defined. Case prolongation of G is Gk is a subspace of whom as k plus 1 is 3 is subspace defined by this is homomorphism from k plus first symmetric power of V to V, such that for any vectors, any k vectors in V, this contraction, this is now elements from V to V, so it's an endomorphism, and this is contained in G. So that's the definition of case prolongation. So for any Lie subalgebra, you can define, you can consider this concept. Nothing mysterious there. And then it's easy to see the following properties. Well, first of all, G0 is just G. And if Gk is 0, then anything above them is also 0. And if you have Lie subalgebras, then the case prolongation of G is subspace of case prolongation of K. That's also easy. And now if sigma is inside case prolongation, then sigma if you contract the first m elements, then it's inside k minus m's prolongation for all m less than k and all m. Okay. So these are very easy to see. The prolongation have this property. It's a very nice concept, very elementary concept. Now somehow you may be surprised why this has never been, why I have never met this. Because it's very natural concept associated with algebra, but people do not meet it very often. There's a reason. So that's the interesting thing. But anyway, so let me now, this is something completely in Lie algebra theory, nothing, no geometry. Let's go to geometry now. Let's consider a projective variety inside projective relation of the vector space V. And then, so this is projective variety. And then I will denote by y hat inside V hat, the affine cone over y. And then for every smooth point, let T hat y be the affine tangent space.
You just mean B. Y is in projective.
Yeah. Now this T hat is affine tangent space of Y at Y. Okay. Now we define the following. Well, it's maybe it's just not really the definition, but anyway, let me auto of Y hat. This is just endomorphisms such that at every smooth point, A Y hat is inside T hat. At every smooth point, the image of that vector under this endomorphism is contained in the affine tangent space. Now this is, you can easily say this is nothing but the Lie algebra for infinitesimal linear operators. So this is just, you consider the automorphism group of the affine cone, linear automorphism groups, and then take this Lie algebra, and that's exactly this line. Okay, so that's the definition. Now the problem I'm mainly interested in is the following. I think this is, I hope that projective geometers get more interested in this problem. So the problem is the following. To classify irreducible, non-degenerate, non-singular variety Y with K. So those varieties which has, I mean, many varieties has automorphism, but I like to know varieties whose automorphism is somewhat extra, that there's a non-trivial prolongation. And we like to, the problem is classifying such varieties among, I mean, if you like, you can include the singular variety too, but, and non-degenerate is rather natural condition. If it's not, if it's degenerate, then you can see that it becomes infinite soon. So, I mean, there are.
So you're only interested in the connected component?
Yes, irreducible.
The origin.
Irreducible? What do you mean?
No, but you're not interested, the group, the variety will have discrete automorphisms.
That's right. I'm not interested in them. I'm interested only in the Lie algebra.
Right, the neighborhood origin.
Yes. So that's the problem. Now, before discussing anything further, I have to give you motivation. Why people consider this, and why it never appeared in algebraic geometry, but still it's important in geometry. It's motivated by differential geometry. So let me explain the motivation from differential geometry. So why differential geometers consider this concept? I mean, this concept of prolongation, they were considered by differential geometers initially. So here's the setting. So let's consider M is an n-dimensional complex manifold. And a closed submanifold C inside projective tangent bundle is a cone structure so that's what I like to define. A cone structure is a certain closed submanifold in the projective tangent bundle on M if projection C to M is a smooth mode. With connected fibers. That's the definition of cone structure. It's kind of differential geometry notion. Of course, it's completely algebraic geometry. As an object, it's kind of algebraic geometry. But it's, we consider the differential geometric aspect of such submanifold inside projective tangent bundle. Now, given such a structure, and for any point x in M, now I define this auto Cx. This is the Lie algebra of terms of holomorphic vector field at Mx, which preserves C. What do I mean by this? Preserves. Let me just draw the pictures. So here you have a manifold M and the point X. And over here we have now the projectivized tangent bundle. Something like this. And by definition, cone structure is just a submanifold inside this projectivized tangent bundle. I mean, something like this. So this is C. This is cone structure. Such that this is smooth morphism. That's cone structure. Now, what I mean by this, vector fields which preserve C. This just means that near here we consider the germ of certain vector fields. Then locally you can integrate to get local biholomorphism. So the local biholomorphism on M lifts to tangent bundle because it sends each tangent vector to some other vector. So this vector field lifts to some vector fields here, and the condition means that these vector fields are tangent to this C. That's the condition, that you preserve C. That's what you mean. This is the equation. So that's this notion. So this, I mean, it's quite possible that this is infinite dimensional, of course. I mean, if, for example, if C is the total product by tangent bundle, then any local vector field preserves C. So in that case, it's an infinite dimensional Lie algebra.
So you're lifting the vector fields from M up to the tangent bundle?
Yes.
So that's like a kind of Gauss.
Gauss? This Gaussman? I don't know what you mean by Gaussman here. It depends. It's derivative. I mean, you are just taking derivative over. Now, what's interesting is this Lie algebra, which can be infinite dimensional, but this has natural filtration. That's natural filtration. So what we do is for each L at least minus bigger than -1, we define OT CX L. So this is Lie subalgebra. Of vector fields vanishing at X to order at least L plus 1. So that's so this is a Lie subalgebra inside this Lie algebra. Then you can see that the -1 part is exactly the whole Lie algebra, because any vector field vanishes to order at least 0, and then it has the it's Lie filtration in the sense that this is contained in. So it's filtration of Lie subalgebra by Lie subalgebra. So it's a Lie algebra, filtered Lie algebra in this sense. Now, the interesting case, then you have got filtered Lie algebra. Then the obvious question to ask is, what is the graded object? And the graded object is exactly related to our prolongation. So the graded object of this filtration is a subspace of the fiber, the L prolongation of the fiber at X, the automorphism of the fiber at X. So that's why this appeared in differential geometry. I mean, this Lie algebra is huge, so usually difficult to study. So we consider the graded pieces. And to study the graded pieces, it turns out that this is inside this prolongation. So that's why it's important. And in particular, when given a subvariety, we have a trivial cone structure. Because for the vector space, the tangent bundle of vector space is nothing but product of vector space with itself. So this contains V cross Y. So this is a cone structure now. So the vectors, when you are given a projective subvariety, it induces a natural cone structure on the vector space. And then in this case, you can see that for each, you have that Y. The equality actually holds. So in this trivial case, the graded piece is exactly the prolongation. So that's why the prolongation is important. So this is when this is, in a sense, the structure which has the largest automorphism is this trivial structure, and in this case, the graded object is exactly the prolongation. So that's the motivation. It's important in differential geometry. For example, when this is a quadric hypersurface, so suppose each fiber is a quadric hypersurface inside the projective tangent bundle. In this case, it's called conformal structure, which is a very classical object in differential geometry, and the corresponding prolongation played an important role in conformal geometry. So that's why it's interesting to study that. But in this setting of arbitrary cone structure, this has not been studied by differential geometry. But somehow it appeared in my I work with more. When we try to use differential geometric method to solve some algebraic geometric problems, this kind of general structure arose, and then you can, to understanding these automorphisms is important, and also the prolongation is important in that sense. So that's why I propose this general problem of classifying projective varieties with non-trivial prolongations. Now you may...
Sorry, I'm failing to understand something. You're saying that somehow, I mean, those vector fields depend on how C varies from one point to the next.
That's right.
And yet your fact over there on the right saying it only depends on the fiber at a given point.
Yes, it only depends on the fiber at the given point. That's right.
So it has nothing to do with how it varies from one point of X to the next.
That's right. But there's a reason behind this. The reason is when there's vector field, which preserves this C, the C must be constant along that direction. Because this is not arbitrary vector field. This is the vector field preserving this cone structure, which means that along that direction the cone cannot change. That's why it's hidden. It's kind of hidden. You're right. But okay, but if this is confusing, it's just as a motivation. You can forget about it. The problem is stated completely in the setting of algebraic geometry, as I did. But of course, when you eventually this appear, I mean this because geometrically that's where the prolongation came from. So you have to use this concept somehow. But let's now go back to just the prolongation problem. Let's forget about this automorphism concept. Now, when you saw the problem I proposed, the classifying smooth varieties with non-trivial prolongation of automorphism, you may consider this is a huge problem. I mean, for each L, probably there are some examples. Seems like a very large class of examples, but it's actually not. And let's consider what's known before. So here's the classical result. The classical result. This is a very special case. So let's consider the following special case where G. This is irreducible representation. Of a semi-simple group. Or semi-simple group. And then associated with such representation, you have the highest weight orbit. So this is highest weight variety. So let's consider this case, because this is a typical example of irreducible, non-degenerate, non-singular variety. So what happens to such highest weight varieties? So in this case, the answer is completely known. And then, first, if this guy has non-trivial second prolongation, then it is known that Y is just projective space. So in particular, there's no higher prolongation, except the projective space, the total projective space, is the only one which has prolongation higher than 2. There's no other variety. So the real interesting case is just one in some sense for this case, for the highest weight variety. And that's the second result. So if automorphism of Y has 0 second prolongation but has non-zero first prolongation, then Y is one of the following. There are 6 lists. First, segregated. following flicker embedding. Flicker embedding of rank 2 Grassmannian in some vector space W inside this. And 3, second varieties. So P2. Hypercoding. N minus 2-dimensional quadric hypersurface inside P n minus 1. And 5 pending spin over. Inside the this is the highest weight for spin representation of SO10. This is E6 Subvarieties. So these 6 are the only highest weight variety. Assuming that this is highest weight variety, these are the only examples which has non-trivial prolongation. So basically, this gives a complete classification among highest weight varieties, those which have non-trivial prolongation. Now, the history is rather complicated. This is proved by Katang, 1909, with some gaps, which was completed by Singer and Sternberg. And Kobayashi. Nagano in 1965. Now this second result is Kobayashi Nagano. In 1964. So this gives, and the proof is completely algebraic. This is the theory of filtered Lie algebra. There's no geometry. It's completely good weights and those arguments with the filter agents. Okay, but now this is very special case, of course. This highest weight variety, they are naturally Lie theoretic object. So maybe that's why you have such nice classification. But then, in general, you have some, still, you can recover part of this in general. So here's the result. I proved with 9 more. In 2005, so that's a long time ago. Now this is the setting where y is as in the problem. So y in PV is now just any irreducible, non-degenerate, and non-singular. And the interesting thing is the first statement holds even in this case. So if the second prolongation is non-zero, then y is trivial. So you see the real problem is first prolongation. There's no higher prolongation in general. So that simplifies somewhat the problem. And for the second result, I need to assume that y is linearly normal. If then there exists y is linearly normal and is different from PV. Then there exists a natural inclusion
projective homomorphism or vector spaces. So the first prolongation is naturally injects into the dual of the vector space. In particular, its dimension is bounded by n. So already this is maybe it's restrictive, but this reasonable condition, linearly normalized. Okay? And under this reasonable condition, we see that the prolongation is very small. Essentially, it's less than the dimension of the vector space. And furthermore, if this is non-zero, then for general y, there exists certain automorphism y hat generating C-star action y with isolated fixed point y and isotropy is the scalar multiplication, is a C star. So at each point you have an isolated fixed point. So you can find, in other words, y has lots of automorphisms. And at each point you can find some C star action with the isolated fixed point at that point, which acts at the tangent space by just C star. So these are what we proved. And well, the second statement is somewhat messy, of course. But the reason I stated it is that it's easy to see that one implies a classical one, and two implies a classical two. This is very easy to show. So this somehow gives more geometric proof of the classical result. And of course, this itself is much stronger because we are not assuming anything about y. I mean, we are not assuming that y is high state. This is assuming y is high state variety. Here we are not assuming this. It's just any irreducible non-degenerate non-singular. And so although this statement is messy, but this is enough to prove the classical result. And if you compare these two results, with our result. So here the proof is completely theoretic, algebra computation. And this is now replaced by projective geometry. Of course, with some Lie theory, because there's lots of group actions coming out, because it's about automorphism groups. So there are some Lie theory, but it's a rather simple Lie theory. Its main component is projective geometry. And in other words, here you have tools like roots and weights. And these are now, in our proof, have to be replaced by tangents, Gauss maps. So it's somehow when you consider certain structure coming from Lie theory, and you try to generalize it to this general cone structure, then you have to replace this Lie theory by projective geometry. So I think there are, in general, some procedure which replace this Lie theoretic data to projective geometry data. And this result is an example of such generalization. And in that sense, it's an interesting result. Now, so the main remaining problem is to classify those irreducible non-singular variety with non-zero first prolongation. That's the main problem. And this shows that there's some hope, at least if you assume linearly normal. And there are heavy restrictions. So it's likely that there's some classification possible. But first of all, I have to say that you cannot expect that the classification agrees with this. So let me explain this. When YP is not highest weight, there are more examples. With non-trivial first prolongation. And these classical examples. So let me give you two examples that I know. Example one. But I think these kind of examples are somewhat familiar to people working on projective geometry, because this kind of example always appear in the extremal examples. So the first one is this scroll type. So we consider vector bundle. PK. And then let Y of this vector bundle. And it's naturally embedded in the space of sections. In this case, as we saw there, the first prolongation is naturally a subspace of the dual of V. So and it turns out that the first prolongation of this guy is exactly this part. So it has a non-zero first prolongation. And this is just one example, but I think there are some other such construction, this scroll type construction, which gives these examples. And here's another example. So let's consider the n-dimensional spinor variety. And let Y be smooth hyperplane section. Then one can show that this guy has non-trivial prolongation. And the dimension is 7. So it has 7-dimensional non-trivial. So, I mean, these are all linearly normal cases. And I mean, for me, I'm kind of lazy. I think for me it's an important problem, but I didn't really try how to go further because it's not easy. And it's not, so far I couldn't even figure out among examples like this, which one really has non-trivial prolongation. So, for example, this may be, I don't know if this is easy or not, but it looks easier than the general problem. Easier problems classify. This type of over PK. I mean, yeah. Okay. These are all negative. This is contained in P. So under this embedding, classify those which has non-zero prolongation. Maybe it's a good problem for like a master student. It's something you can check, but maybe difficult, maybe easy. I don't know. But certainly it's easier than the general problem. And also classify linear sections of this 1 to 6 hyperplane sections, or further 2, 3 more hyperplane sections, linear sections of this with non-trivial. Even these I haven't really tried. And we need to figure out just how many there are so this maybe is really worth carry out this easier problem, just to figure out how many there are. But I expect that there are not so many. Now that's about the general problem, and now in the remaining few minutes, I will explain at least the first result, how this kind of result can be proved, just to give you the idea. The point is you have to use this projective geometry somehow to prove something like this.
Excuse me. There's a relation between the non-vanishing of the first prolongation of a projective variety and its hyperplane section is not known.
I don't think, I cannot say whether it's difficult or not because nobody has looked at it. But as far as I know, it never appeared. Maybe somebody guy knows, but to me, it's not known to me. And it's I don't think it's trivial. As far as I know, even the relation between just automorphism of a variety and its hyperplane section is not so simple. Okay, so sketch of proof. Just let you taste the kind of argument we use. The main thing is the following main lemma. So we want to extract some geometric information out of this prolongation condition. So y in PV is as in theory. Now suppose you are given an element of the first prolongation. Suppose it is given. What kind of geometric information does it give? Does it give us? That's the problem. For each vector inside the affine cone, we can consider this sigma. You see, sigma is just the S square V to V, right? So we can consider sigma, alpha, and alpha. This is an element of V. Right? Just S square V. And it turns out that this is the sigma alpha alpha is in fact is included in this set. That's the first lemma. And second, if sigma alpha alpha is 0, so alpha, then sigma. That's the second one. And this main lemma looks very simple, but this is turns out to be the key to the theory. So let me tell you why this implies theorem 1. So main lemma implies theorem 1. So this is roughly how it goes. So suppose you are given tau S3 B on alt element. The second prolongation. Now you assume y is not PV. And we want to show that any such tau is 0. That's the statement. Okay. Now how to show this? I'll consider that for each beta in y hat, consider sigma, which is tau beta. And by definition, if you put beta there, then this is now inside here, the first prolongation. And then by lemma 1, sigma alpha alpha is inside C alpha, but on the other hand, by the very definition of this beta here, this is inside T beta. So that's the kind of argument. That you put two different alpha and beta, then there's a relation between their tangent vectors somehow, two different tangent vectors. There's some element here contained in both of them. And here you use result of like Jack theorem on Gauss map, finiteness. And you can see that this implies that sigma alpha is 0. Because it gives there's a non-trivial intersection between this tangent space intersect this vector itself at different points. And if it's possible at every point, this must be in the kernel of the differential of Gauss map, which must be 0 by this finiteness. So this is 0. And so this is how you use projective geometry to argue. And then once you get this, then now lemma 2 shows you that since this is 0, sigma is 0 for any beta, so this is the tau. So it's a rather brief, but that's the rough idea how you use projective geometry to prove something like this. The main point is this main lemma. So it looks very simple, but it's actually very difficult to prove. Especially this 2 was the hardest part of the whole proof. It looks easier than the first one, but actually it's quite difficult. So let me just give you an idea how one prove that. This other main lemma. The main lemma 1 is easy. So I skipped it. I'm not saying it's rather easy. And the main point is 2. We use induction and dimension 3. So it's rather somewhat involves induction. So in other words, what you say is theorem 1 for dimension n most n minus 1 plus main lemma for dimension. These two implies main lemma. That's how you proceed. So you use this rather involved induction. This part and this part together imply this, and then this implies theorem 1 for dimension 3. Yeah? So you can now go to the next step. So that's how the induction works. Now, why this kind of induction is needed? So the key idea is this. Idea is using, so what you have to show is this. Sigma alpha equals 0 for all. You have an object like this, and you like to show this is 0. How to do this? Assuming this is non-zero, these automorphisms gives actions on Y with orbits. Orbits are lines. You can check that this endomorphism induces an automorphism Y whose orbits are that's lines. And then you consider construct cone structure. C by taking tangents to these lines. Then apply this theorem 1 plus main lemma for dimension E to this cone structure. So just to finish it, let me draw the picture of what kind of induction this is. So what's going on is you have a big projective space, and you have this variety Y. And what you do is you produce certain lines using this weird prolongation element. You produce certain lines here on Y. And then using these lines, you produce here, at one point here, you produce P and this yellow guy, another yellow guy here. And this yellow guy is just tangents to these lines. So the induction goes from this big projective space and submanifold to this tangent, the projectivization of a tangent space to this submanifold here, determined by these lines. And then you go further here. Now you produce lines over here and go to the tangent space here. So the induction is from the ambient space to the tangent space. That's how the induction goes. So that's the proof. Thank you.
Thank you for your talk. Are there any questions?